Hello, welcome back to the Sudokult discussion. And today will be part 2 of our set series, which has an unknown number of episodes, but I think we'll be doing at least one more. And in this episode, we'll be covering some more advanced uses of set and some more interesting uses of set. And it will be entirely focused on set rather than talking about MSLS, which was actually probably the majority of last episode. So I'm David Rangsk Clamage, and with me,
Philip Newman.
All right, and Philip's going to be doing most of the talking as usual, but I'll try to chime in and ask the questions that are on people's minds. And I think what we're going to start with is the puzzles from last time that
right.
Philip challenged everyone with. So we're going to go over what the solve path is for those, or at least the break-in.
Yeah, so the first one was our guest puzzle by Jovial, classic Sudoku number 4. I don't know if she gave this a name at any point after. I got people started on naming things. So, so this is just a basic usage of set. I don't remember if we went over this one last week in particular. There are a lot of odd digits aligned in these rows. Just highlight all of them. And use orange for odd. And there are a lot of even digits aligned in these columns. So we're going to use those for our set. And this one's pretty straightforward. There are 10 odd digits in orange, and there are 10 even digits in blue, and there are 20 total cells in each. And since they contain the same digits, we need 10 even digits in orange, and we need 10 odd digits in blue. So you can fill in odd digits for all of the remaining blue cells, and you can fill in even digits for all the remaining orange cells. And I'm not going to go into the basics after that. This puzzle pretty much falls apart after set, but it's intended as a demonstration of one basic set idea.
Yeah, and this is one of the checkerboard sets. I think you can sort of offset the checkerboard as well, but it's a pretty popular set to use, is this checkerboard pattern. Because
this one in particular is pretty popular because it's balanced, unlike the other checkerboard that we showed. With all the odd rows and all the even columns.
Right.
But you'll see both. All right. The other puzzle was this guy. This one is not a basic set. I don't know if anybody has even tried this puzzle or solved it. Let us know in the comments, I guess. But I'm going to go over the solution. This started as an exploration of set after... It was after one of Sam Kappelman-Line's puzzles that was on Cracking the Cryptic, and this was before set was even named. It's demonstrating MSLS, but Simon used the basic checkerboard pattern. So I'm going to highlight that first. I'll do that in orange. And highlight these in blue. And let's get rid of all of the overlap. So in Sam's puzzle, you did this checkerboard, and there were a bunch of odd digits in orange and a bunch of even digits in blue, just like the one we looked at just now. And there were no degrees of freedom. And so if you recognize that, you could fill in all the odd digits and all the even digits. And there was a single that emerged somewhere in the grid, and the puzzle solved. So I was playing around with ideas like this, and I was wondering, what if you did have degrees of freedom? Are there ways to get rid of those degrees of freedom without giving more digits in the set. So in this particular puzzle, in our orange partition, there are 11 of the digits from 2, 3, 5, 7, 9. When I was making it, this was odd digits, but I swapped the 1 and the 2 because I like to put my digits in order sometimes. So there are 11 of those. And in blue, there are only 6 from 1, 4, 6, 8. So we actually have 4 degrees of freedom. That seems like a lot, and that seems like this must be completely useless if we have that many degrees of freedom.
Yeah.
We have 14 places for 14 empty cells in orange, and we need 10 of these digits in orange. We need an extra set because that's imbalanced. So how can we resolve those degrees of freedom? Well, obviously, that's what the other given digits are doing. But how are they doing that? Have any ideas?
Well, they're restricting where those extra digits can go, it seems like.
Right. So in this box, we already have a 1 and a 4, right? And we have 4 orange cells. So what's the most number of those digits, 1, 4, 6, 8, that we can put in those orange cells in box 1?
Right, we can put 2 of them.
We can put 2 of them. So we don't know where they are, but 2 of these orange cells at least have to contain another digit from 2, 3, 5, 7, 9. So that's taking up 2 of our degrees of freedom. We don't know which ones, but we know there are 2 more of the orange digits in orange in box 1. The same applies to box 9. There's a 4 and an 8 already in the box, not in orange. So we could put a 1 and a 6 in orange, but the other 2 orange cells, at least, are going to have to be from 2, 3, 5, 7, 9. And that got rid of our 4 degrees of freedom. So the conclusion in this case, we have to be a little careful with boxes 1 and 9. Outside of boxes 1 and 9, we can conclude that all of the orange cells are from the blue digits. So these are all from 1, 4, 6, 8. And we can do a little cleaning up. This can't be a 1 or an 8, etc. I'm not going to worry about that right now. All of the blue cells, again, outside of boxes 1 and 9, have to be from 2, 3, 5, 7, 9.
What about the one in box 7?
Oh, I missed one. Okay. And actually, if we're looking at box 1 and box 9, those do as well. Because if we had, say we had a 6 here in box 1, well, now we only can put 1 of those digits in orange, and we have an extra in blue, so that's going to be problematic. We can't quite fill in the orange cells in boxes 1 and 9. We know that 2 of them are, in box 9, 2 of them are 1, 6, and 2 of them are from the other digits. But what we can say is that the white cells can't be 1, 6 either, because they're in orange somewhere. And we can do the same thing up in box 1. So those are all the cells that are affected. And from here, again, there are singles. I'm not going to spend the time going through getting rid of pencil marks. This can only be a 7 or a 9, for example. There's lots of that. Eventually you'll find some singles and some other basics that resolve this puzzle. But this was sort of my first exploration with almost set. And this is actually almost set.
So can I take a step back, and because I feel like I think I understand it, but I wanted to let you finish the whole explanation before I ask these questions. But sure. I want to take a step back and ask about the orange stuff again. You can leave your pencil marks if you want, because I feel like it's almost clicking, But if I'm almost clicking, then I feel like a lot of people watching this are going to be like, I have no idea what he just said.
Sure, so, it's worth going over it again.
Yeah. Let me try to explain it myself, because I think that'll help me really get a grasp on it. So
okay.
The orange digits. So we can sort of say the orange digits and the blue digits, because whenever we do set, we're always segregating the digits between the two sets that we're comparing.
Right.
If those digits weren't segregated, then we could just eliminate them from both sets.
Right.
Excuse me. So let's count the. I guess let's start with the blue digits. So there are 6 given blue digits.
6 given.
And because it's an imbalanced set, we know there's at least one more of those givens also in orange. So because there's 4 distinct digits there, we're talking about 10 total digits.
Right.
And if we were to count the empty orange cells, we count 14 of them. Is that correct?
That's correct.
Okay, so I'm getting that much so far. So at that point, it feels hopeless, like you said. But it's not, because we can make an observation. And that observation is, in box 1 and 9, 2 of the orange cells in each of them cannot be from 1, 4, 6, 8.
Right.
Specifically in box 1, the 1 and 4 are already used. And in box 9, the 4 and the 8 are already used. So whatever is going to go in 2 of those orange cells in each of those boxes, it's not a 1, 4, 6, 8. Therefore, those aren't actually degrees of freedom. Where it uses up those degrees of freedom.
And another way to look at it, we had 14 orange cells, but 4 of them are in box 1 and 4 of them are in box 9. That means we have 6 other orange cells. So if we think about where we can put those 10 digits, we can put 2 of them in box 1, we can put 2 of them in box 9, and we can put 6 of them in the other 6 cells. And that's our 10. So we can't do any better than that, so we have to do that.
Right. That makes sense. And I think you might have gotten a little ahead of yourself when you first started explaining, because you were talking about box 1. You're like, we can put a 6 and an 8 in the origin box 1, and then we're implying that you had to, but you hadn't proven yet that you had to.
Yeah.
Until we then visit box 9 and see that uses up the other 2 degrees of freedom. So.
Yeah, a lot of times when you're talking about set or MSLS last week, you're looking at how many you can get away with putting somewhere, and then you're looking at how many you have to put somewhere, and finding that the most you can put is equal to the least you need to put. So that's where your deductions come from.
All right, yeah. So that all makes sense. Now, without those givens, this would have been a useless set, right? We wouldn't be able to get anything from it.
Right. And I mean, it's only 17 digits, and we know there aren't that many puzzles that only have 17 digits that are classic.
Yeah.
So that's not too surprising. But when you're looking at when you're setting a puzzle, one of the things you can consider if you're trying to set a puzzle with set, and I'm going to say set a lot in this sentence, you can think about how many digits you need and how you're going to divide them up. So if we go back to Jovial's puzzle, the blue and the orange regions have 20 cells. In order for this set to have 0 degrees of freedom, we need 20 digits, right? We can divide them up however we want. We don't have to have 10 even and 10 odd. We could have 11 even and 11 odd. And in fact, in this case, we don't have to count 9 as odd. We don't have to put it in the orange set. We could say there are 12 of these digits, and there are 8 of 1, 3, 5, 7. And that works too.
Yeah, that makes sense.
In the case of imbalanced sets, you have to be a little more careful about how many digits there are. There is a way to work this out without actually doing the counting. That was Phil that I referenced last week. I'm not going to go into that because it's not really that helpful. But
help Phil.
what you can determine is that with this particular set where you have 25 cells in orange and you have 16 cells in blue and you have 5 orange digits and you have 4 blue digits, you need 21 total digits. And that's what we worked out, essentially. We had 17 and we were 4 degrees of freedom short.
Gotcha.
So in any puzzle, in any Latin square puzzle, this doesn't even have to be Sudoku, the orange, whatever 5 digits we want to pick in orange, and whatever 4 digits we want to pick in blue, if we count those up, the orange digits that are in orange and the blue digits that are in blue, there will always be 21. That's just what the solution is going to look like. Now, whether you can use that or not depends on how the digits are laid out. You could have a puzzle where all of these cells are empty, and so this particular set is completely useless. You got to look for something different. But that's just a property of every Sudoku grid. Just like the Fistamethel ring it's always the case that the ring equals the 2x2 corners. It's also always the case that these sets will have a certain number of digits in them. And it's coming from the idea that they're the same up to complete sets of 1 to 9.
So when you say 21, what are we counting exactly when we're counting 21 digits?
Counting the number of given digits that you need in orange and blue that are from the corresponding partition when you're setting the puzzle. It's true in the solution as well. It's most useful when you're setting the puzzle. So in the solution, if I count up the 2, 3, 5, 7s, and 9s that are in orange, and I count up the 1, 4, 6, 8 that are in blue, there will be 21 of those. I don't know where all of them are. Actually, I kind of do. I know the other orange digits from in the orange cells are in boxes 1 and 9 because we determined that's where our degrees of freedom are being used. And we might get into that a little bit more, the idea of where that degree of freedom is being used, but that's what it's counting. When you're solving, the most useful thing is how many digits do I have in blue and how many empty cells do I have in orange, or vice versa. Right,
and if it's imbalanced, then you need to look at the number of digits.
Yeah, you need to account for that. That's why you end up with this kind of strange seeming 21 number with this particular set. It's because of the imbalance. If they're equal, it's always going to be the number of cells in the set. So, okay. So, anything you wanted to add on that?
Can we count the 21 that are here?
Yeah. So, we counted 11 of the digits 2, 3, 5, 7, 9. Mm-hmm. Right? And we know there are 2 more in box 1 somewhere. And we know there are 2 more in box 9 somewhere. So I guess it gets us to 15. And then 16, 17, 18, 19, 20, 21.
Okay. Now, if you gave more than 21, that would just, well, would that not just be like telling you where the equivalent is from the other side?
You can't give more than 21 orange digits in orange plus blue digits in blue.
I see. Okay.
Yeah.
If
there
there's
will
an
always
orange,
be exactly 21.
If there's an orange digit in blue, we aren't counting.
Right.
Gotcha.
Yeah, what the set is telling us is that there needs to be these orange digits in blue everywhere.
And how do we calculate that 21 number? Is that what fill is for?
That's what fill is for.
Okay.
So fill stands for Phil's Helpful Intersection Limit. So this is just something I came up with messing around. So if you want to know the formula, you need to determine what digits are going to be in orange and what digits are going to be in blue. And the way I was doing this, this was back when we were taking more of an intersection approach rather than a set approach. But what you can think about is there are 5 rows and there are 5 columns in orange.
Okay.
The orange cells are the intersection of those rows and columns. And then blue is... I didn't highlight right.
You need to be in color mode.
Well, doesn't matter. In blue, there are 4 rows and 4 columns. And the blue cells are the intersection of those. We also need to know how many digits are in each partition that we're considering. So in this case, we're considering 2, 3, 5, 7, 9 in orange. So again, 5 digits. And 4 digits in blue. So the formula is the 5 rows times the 5 columns times the 5 digits in orange plus the 4 rows times the 4 columns times the 4 digits in blue, all divided by 9.
So 5 cubed plus 4
5 cubed plus 4 cubed, in this case. Yeah. Okay. Now, if we went back to this example, it would be 5 columns times 4 rows in orange, and 5 rows times 4 columns in blue. And those are both 20. So then when we multiply by the digits that are in the set and then divide by 9, that's going to cancel out. So that's how we end up back at 20.
Now, if you were going to start using boxes, like for the Fisto ring, for example, is that kind of...
Then it doesn't work. And I haven't really gone back and considered whether you can do something like that. At that point, it's easier to just think about how many digits are in one set versus how many empty cells are in the other set.
Gotcha.
And you can make a calculation that way.
That might be easier anyway, regardless.
Yes, it is always easier, and I never count them like this. I just happen to know, in this case, it's 21.
Okay.
If there are 5 orange digits and 4 blue digits. It changes if there are 6 orange digits and 3 blue digits. So you're multiplying by something different.
Right.
But, yeah. So that's Phil.
I made you explain it even though you didn't want to.
Yeah. Well, nobody's going to use it. But it's a cute little formula.
Yeah, it's cute.
It's kind of elegant. So I like it. All right. So one thing I wanted to do really quick. Last week we talked about some common set arrangements. And this is another one, this sort of offset checkerboard pattern. That is really common because they're equal.
Yeah.
This is one I forgot to mention. This is Tattooing Sunset. And this pops up in a lot of the tattooing puzzles. Where you will have 3 columns and 3 rows. All in different bands and stacks. I totally just highlighted the wrong thing.
I was going to say, what is that? This feels more familiar.
I was trying to talk and do something at the same time, and it didn't work.
It's difficult.
Yeah. So what we have then is these 9 digits in orange and these 9 digits in blue. And in this case, it doesn't work. Because there's 2 8s. So you actually need something a little different in Tattooing Sunset. But this sort of general idea comes up a lot in the tattooing puzzles. This one, I don't actually remember off the top of my head how you can fix it. Probably by adding something to blue. Anyway, I'm not going to spend the time figuring it out.
We'll leave that to an exercise to the viewer.
You can do this with set. But a lot of the tattooing puzzles, you can look at the digits in one direction versus the digits in the other direction that are offset. And you can figure out how to get that one more degree of freedom somewhere. But it's something to keep in mind. This is the obvious thing to try in this puzzle. But you need to remember that you've got to look for duplicated digits.
Right.
Those are going to get in your way. So keep that in mind. And yeah, if you want to look for this in this puzzle, I don't remember it off the top of my head, but that's okay.
Maybe it has to do with the last row since there's givens there.
Yeah, I'm sure adding 2 to blue or adding these to orange somehow, it works out.
All
right. So mostly so far we've talked about set with rows and columns. The Fistum FL ring, we did use boxes for that. I wanted to show this puzzle again. This was our Frankenswordfish puzzle.
Right.
Basically any fish puzzle, well, any fish, any basic fish, any Frankenfish, any mutant fish that we talked about in the fish episode, you can look at that fish as a set argument. So our basic swordfish, let's bring up our sandbox here. Our basic swordfish is looking at, say, the digit 1 is limited to those cells in these rows. So if we color our rows orange, and we color the columns that are covering them, these are the cover sets in our fish, blue, now what we're saying is the blue digits and the orange digits are the same, right?
Yes.
But the rows told us that there are no 1s outside of the white cells, right?
Yeah, so 1 can't be an orange at all.
1 can't be an orange at all, so 1 can't be a blue at all either. So it's getting the same eliminations as the swordfish.
Right.
You can do that with tuples, and you can do that with any fish, as long as it doesn't have fins. We'll get into fins in a little bit. But that includes Frankenfish. So I just wanted to show that real quick. So in this puzzle, there were 2 Frankenswordfish on 8 and 9.
Right.
In the same place. And so our base sets were these rows. I'm just going to mix up whether I'm using blue or orange. And at some point I have red highlighted instead of orange. So hopefully that's not too confusing. The cover sets. So just in general, when you're doing set, and this is a good way to find fish too, you want lots of digits in your set, right?
Yeah.
So when I'm looking at which columns or which boxes to add to orange, I want to get rid of the empty blue cells, because that's going to get rid of some of my degrees of freedom, hopefully. So just like with the fish we were covering these columns, covering the cells with the columns, and covering this box, we do the same thing with set.
Yep.
So we've done 3 rows in blue, we've done 2 columns and a box in orange, so we have a balanced set.
And blue is all givens.
There are no 8 and 9s in blue.
Yeah.
Yeah. So we can conclude there are no 8 and 9s in orange. And that's exactly the same deduction as the Frankenfish.
It's almost like easier to understand when you talk about it in set form.
Right. It tends to, well, it depends.
It really does, but
some basic fish are easier to find as fish.
Yeah.
If there's just one. When they start to overlap a lot, set is probably the better way to go.
That's kind of my methodology as well when I'm solving, is if I find like a fish, then okay, I'm just using the fish. But if I start finding a second or a third fish, I go, there's probably a set representation of all this, especially if they were all in similar rows and columns. And then I go and look for the set, and often that just finishes off the puzzle right away, rather than having to find the 7 or 8 fish that the setter put in there.
Yeah, and we talked last week about multi-sector lot sets in Masalas. There's also the term multi-fish, which I don't know exactly where the line is between the two. They're both rank 0 logic, where we have a certain number of things that we need to meet and a certain number of things we're covering them with, like our base sets and cover sets, like our truths and links, that sort of thing. But yeah, it's the same basic idea of we have a bunch of fish, we're going to combine them into one thing, and it's going to make it simpler.
Yeah.
Set just kind of takes care of all of those different specific named things and does it a slightly different way. That's what that looks like. All right, moving on. So this is another puzzle that we looked at previously. This one has finned fish.
Ah, yeah.
So we're going to talk about how to use set with fins. So, where's our set in this case?
Can I remember? I think that the almost 3x3 grouping of givens is key.
Yep.
So
blue or orange?
Let's go with blue.
Okay.
Now the question is, how do we capture those? Is it the 3 columns or the 3 rows that we're interested in is the question. Does it matter?
Doesn't matter.
All right, so let's just go 3 rows then, since you have your mouse there.
Okay. Let's start with that.
And then, like you said, we want to get rid of emptiness. So what about those 3 empty columns? There's actually a 4th empty column as well on the column 9, but I don't know if that's useful.
Go ahead and do those.
And then maybe we want to add the row 1 to blue.
Yep.
So I didn't know ahead of time what those would be, but maybe that's helpful to people for coming up with a strategy of what set to pick.
Yeah. So you're looking for lots of overlapping digits. In this case, it's the high digits and the low digits.
Now, was this the one you intended me to find, or?
So there's kind of 2 that you can use. The one I have in mind, the one I had in mind when I set the puzzle, is that.
So it's imbalanced.
So it's imbalanced. That's okay. We can do imbalance.
Okay.
The reason I like this one a little more is there's just not much in blue to consider. There's one empty blue cell.
I like that too.
Yeah. But you can use the other one. It's balanced, and there was a separate solution path to this. It was a little bit different, amounted to the same thing. Laren came up with this.
Mm-hmm.
I don't know if that's how you pronounce their name, but that's what we're going with. And it was a really cool argument. I'm not going to talk about it tonight, but it was neat. So we're going to focus on how to convert the finned fish into set.
Okay.
So I kind of call this finned set.
Good name.
So this was our fin in our fish,
mm-hmm.
if you remember. We can just look at one of the digits. Let's look at 2. So in the rows that we've highlighted in blue, where can 2 go? It can't go in any of the blue cells except possibly this one.
Yep.
And it can't go in these cells.
Right.
So I'm just going to highlight these real quick. It can go in those, and it can go in this fin. So the deduction with the fin set is if the 2's not here, I have a jellyfish.
Right.
In green. So that means I can't put 2 in the other cells in those columns, which all happen to be orange. That's not a coincidence. Set and fish are just kind of inverted from each other. If this is a 2, though, we don't have a jellyfish, but we still can't have a 2 in those cells because they share a box. So these cells can't be 2. Okay?
So can we take a step back and talk about... So there's 1, 2 in orange.
Yep.
Okay, I think I'm understanding this a little bit. But now that I'm explaining it, but I'll continue explaining it, because if it took me doing that, then... we're trying to figure out where 2 goes in blue, because 2 is not in blue already.
So no, not quite.
Or
so it's imbalanced, right?
Right. Okay. So let me put it another way. 2 could go in blue, but it doesn't have to, because we're imbalanced.
Yes.
Yeah. If it were good to go in blue, there's only one empty spot that it could go. So either it's not in blue at all, in which case it has to be in green somewhere.
Right.
Or... And only once in green? Or is that...
No. So it needs to appear 4 times in these rows, right?
Right.
So if it's not in blue, it needs to appear in
those
green
are the only places in those rows it can go.
Those are the only places. So that's our jellyfish version. Yeah. So let's remove that.
Do you have like a different way to look at this?
No
with
confusion.
that, or is that...
Yes.
Okay.
So what you were getting at is exactly where we're going.
Oh, okay. I see.
So there's a couple of different ways you can look at it, but sticking with this version. This is our fin in set as well. So this cell could be a 2. Because this is an imbalanced set, though, if this is a 2... we need 2 2s in orange. And we only have 1 currently.
Yes.
Right?
We need at least 2 2s, right? Or does this match up? We didn't count like how many blues must go in orange, right? Or I guess it doesn't matter.
It doesn't really matter.
Okay.
Yeah. And it's not super relevant for this case anyway.
Okay, so we're an imbalanced set. Sorry, I'm wrapping my head around this. We're an imbalanced set, so we know there's at least one set of 1 through 9 in orange somewhere.
Yeah,
there has to be exactly one of 1 through 9 somewhere in orange.
Yeah.
And then in addition to that, there's all the digits in blue.
Yes.
So if that remaining blue were a 2, then we know there's another 2 in orange.
There's another 2 somewhere in orange.
Yeah.
Now, that doesn't really matter. For this case, what we care about is it's not in those, because it shares a box.
Okay.
But it's worth mentioning, if there's a 2 here, there has to be a 2 somewhere in orange.
Yeah.
And it's not in any of these or these or these. So actually, it has to be in one of those 4 cells.
Wow, that's actually pretty limited.
Very limited, yeah. So that's one case. The other case is this cell isn't a 2. It could be a 3, say.
Okay.
Now, we don't have any 2s in blue. So this 2 must be from our extra set of 1 to 9, and we don't have any more 2s in orange.
Yeah, we're not allowed to put any more 2s in orange at all.
Right. So again, we don't have any 2s in these cells.
Right.
Okay? Now, the way to look at it as set versus looking at the digits individually, because what we just did there was basically the fin fish again, right?
Right.
We're going to look at all of the digits 1, 2, 3, 4.
Which aren't in blue, other than possibly one of them could be.
Right. So, we don't have to have any of the digits 1, 2, 3, 4 in blue.
Right.
But at most, we can have one of them. And if we have a 1, 2, 3, or 4 in blue, that digit, whatever it is, isn't in these cells. If we don't, and this can't be all of those digits,
right.
Obviously, but it doesn't matter.
Can't be most of them.
Yeah, it could be a 7. If that's a 7, then we don't have any digits 1, 2, 3, 4 in blue, so we can't have any more in orange.
Right.
So this has 1 degree of freedom. And in this case, just like with the fin jellyfish, that 1 degree of freedom causes us to lose a lot of our eliminations. But because that 1 degree of freedom is restricted to one cell, our fin cell, we can make some deductions about where it overlaps with the other set in the box.
Yeah, so if it's from 1, 2, 3, 4, whatever it happens to be is just naturally eliminated from those red cells. Yeah. And then also, the other 3 of those digits now doesn't appear in blue at all, so they're also they're not in any of the orange cells.
Yeah, that's worth mentioning as well. If this is a 1, there is another 1 in orange, but it can't be here.
Yeah.
But also, we can't have a 2, 3, or 4 in orange again, because they're not in blue now. So
yeah,
it is worth clarifying that. All right. The other way of looking at this.
Oh, there's another way.
The other way is to add this box to blue.
Okay.
And now we're double counting that fin. But we have a balance set. Right?
Right, yeah, because we just removed one set from orange and added it to blue.
Yep. Well, yeah. We added the box to blue.
We added the box to blue. Okay.
Yeah. So blue is now 4 rows and a box, and orange is 5 columns. So balance it.
Gotcha. Yeah.
Same number of cells, as long as we're remembering to double count.
Maybe make it purple or something.
Yeah, that's a good idea. That's our fin. So we can use this in the same way, but now it's actually a little easier. We need a 1, 2, 3, 4 in blue now, right?
Mm-hmm. Because we're no longer
blue cells. Yeah.
Yeah, we're no longer imbalanced.
Right.
So we can't use that extra 1 to 9 set anymore. So there is a 1 through 4 in orange, so there must be a 1 through 4 in blue as well.
Exactly. So now we have to have 1, 2, 3, 4 in blue, and these are the only blue cells, and they're all in the same box. So wherever they are in here, and they could be here, in which case we have 2 effectively in blue. So we need another one in orange, but we don't care about that. What we care about is 1, 2, 3, 4 are in those 5 cells somewhere. So they aren't here.
Yep.
So the net result of this is we can't have 1, 2, 3, 4 in these cells. And we end up with 7 right there. And a 6 right there. And so on. And it collapses.
And it's exactly the same deductions, even including having 2 of the fin in orange.
Right.
Which is, I mean, it should work out that way because it's logical, but it still feels surprising and cool that it does anyway.
It happens a lot with Set where if you don't have any digits in a house, then it doesn't matter if you add or subtract that house.
Right, that makes sense.
Or even if you have 1, I don't know if you can do it here, but there's a 3 here in orange. In some situations, we could add this row to blue, and it wouldn't actually change the number of degrees of freedom. I don't think it's the case here, but in some cases it could be.
Okay.
It has to do with how many empty cells you're adding to the other set and how many you're getting rid of. So in this case, we would be adding a lot of empty cells to blue and getting rid of 2 orange. So that's not good. We want as few empty cells as possible, so we don't have the degrees of freedom.
Yeah, just in total for both sets, how many empty cells you want to minimize.
Right. In this case, though, we're effectively adding 4 cells to blue, and we're subtracting 4 cells from orange. We're also double counting this cell, but it's the same cell. It doesn't matter so much in this case. It's also part of the bigger set as far as the digits go. So that does make a difference. Okay, so that's one way that you can use what we're currently calling almost set.
Yeah.
So 1 degree of freedom in your set. if that 1 degree of freedom is very restricted to one cell or maybe a couple of cells in the same house, you might still be able to make some deductions on the cells in the other set that share that house.
Gotcha.
All right. What do I have next? I have a contrived example. You can't see my titles, but this says contrived example number 8 on my screen. You can see them, but
I can see it.
The audience can't see
Audience cannot see it.
So I've been naming all of my contrived examples like this, just for fun. So this is an example of a continuous nice loop. So we're going back to our first episode on alternating inference chains. Hopefully everybody did their homework and remembers how all this works. Do you see the alternating inference chain or the continuous nice loop in this puzzle?
Well, we've got the strong link between the 1 and the 2 in box or in row 1, column 1. And then we have, I guess we could go either way, but we could go down to row 9 and say that there's a weak link between the 1s.
Here.
And then there's a strong link to the 1 because 1 is limited to 2 places in that row.
Yeah, there's a 1 here. So I've pencil marked them even though they're not in the same box.
And then in that cell, there's a weak link between the 1 and the 2.
Yep.
And then there's a strong link between the 2s in column 9.
Yep.
And then there's a weak link from the 2 back to our start.
Yep. So that gave us a continuous nice loop. And if you remember from our first episode, whenever we have a continuous nice loop, it effectively turns all the weak links into strong links and all the strong links into weak links.
Yep.
So in particular, this 1-2 weak link becomes a 1-2 pair. And that's enough to solve this puzzle. There's 3. Well, I say solve this puzzle. It's not a complete puzzle.
It's not a complete puzzle. Don't try to solve it.
It's enough to solve the puzzle that this example is based on.
Right.
This is not. It doesn't have a unique solution, but in this case, it's enough to give that 3 there. All right, so let's backtrack. What I want to show off, this is something kind of new, and I haven't really done a whole lot with this yet. The best way to find this deduction in this puzzle is exactly what we just did, the continuous nice. But one of the things we were curious about is, can you express those in terms of set? And so I was thinking about some other continuous nice loops that we know.
Right.
Such as the X-wing. The X-wing is a continuous nice loop. We have a strong link in a row, a weak link in a column, a strong link in a row, weak link in a column. It makes a nice little box. And we make eliminations based on that.
Right.
Well, we know the fish can be expressed as set. So I thought, how do we do that? How do we actually turn the fish into set? And what we usually do is we put one of our links, our strong links or our weak links, into one color, and we put the other into the other color.
Right.
Now, in this example, with our swordfish,
right,
these aren't strong links in the same sense, but you can kind of think of them as a tri-value strong link, sort of.
Sure.
One is in one of these 3 cells.
Yeah.
Right. And these are our weak links.
Right.
At most, 1 is in those cells.
And to be honest, if I were to start experimenting with whether set works or not, the first thing I'd try is just highlighting those rows and columns and seeing what happens.
Right. So, I think I went too far. There we go.
A little preview of what's to come.
Preview. So, can we do the same thing here? That was the question.
Yeah.
So let's try it. And we're going to run into a problem immediately. This strong link is in a cell. So what do we highlight?
Good question.
Good question. So this is what I came up with, and it seems to work.
Okay.
in the examples I've tried it in. This is definitely an area that needs more exploration.
Gotcha.
But it seems to generalize any continuous nice loop, even ALS nice loops, like the ALS XZ ring, using set. So let's put our weak links in blue, say. So we had a weak link on 2 here. And we had a weak link on 1 here.
There.
Right? So we're double counting this cell.
Right.
Put it in purple. And our other weak link is here, right?
Yes.
So we don't know what to do with that yet.
No.
So we'll come back to it. So strong links, we'll put in orange. So strong link on 1 in this row. Strong link on 2. And again, we're double counting. So I'm going to mark that in red.
Yeah.
And we'll get rid of those. All right. Any idea now what we might do with our other 2 links that are in cells?
I mean, there's the boxes, but...
There's the boxes. So my idea was we had a weak link in a row.
Uh-huh.
And we had a weak link in a column intersecting in that cell where the strong link is, right?
Yeah.
So let's add the other house, which is the box in this case, to orange. So that gets rid of those. And now the orange and the purple cancel out. So this is just back to being singly counted in blue.
Right.
We'll do the same thing down here. Put that in blue. Get rid of these. Get rid of those. So that's our set.
Interesting.
All right. So now, how does this work as a set?
Yeah. Do we still need to use the strong links that we found?
Not exactly, no. What we're doing is effectively going to use them, but
Okay.
hidden as set, basically.
So one thing I am seeing is the conveniently placed 1 in box 8 and the 2 in box 6, which eliminate those from a large swath of our empty orange cells.
Right. And you'll notice, let's take the column for example. The set that we've chosen, because blue and orange intersected here, we got rid of that cell that could have held 2.
Right.
These were givens, and these are covered by this 2. So we really only need to think about this cell at all when it comes to 2. But just as an example, let's put a 2 there.
Right.
So what does that mean in terms of set?
Well, we need a 2 in orange now.
Now we need a 2 in orange. It can't go here.
No. So it's going to be in row 9 somewhere.
All right. Can it go here?
I don't immediately see why it couldn't.
All right. Let's say we had a 2 here. Where does 2 go in box 9?
Into blue.
It goes in blue.
Now there's another 2.
Now we need another 2 in orange. So putting a 2 in some of the orange cells puts another 2 in blue. And that's not going to work. So if this is a 2, that's a 2.
Okay. This feels almost stronger than what the continuous nice loop is telling us.
It turns out to be the same.
Turns out to be the same? Okay.
It feels pretty strong. But that's because we were assuming what this digit is.
Okay.
So let's try it as a 1.
I feel like it's exactly the same.
Exactly the same.
Yeah.
It's a diagonally symmetric
Yeah.
setup. So 1 can't go here. If we put a 1 here, it would rule out 1 from those. It can't be in those. It's got to be in blue. So we would end up with something like that with 2 1s in blue and only 1 in orange. So that doesn't work either. We would need a 1 there. So what we found is whatever we put There we go. Whatever we put in row 1, column 1 also has to go in row 9, column 9. Therefore, it's a 1-2 pair.
Right, but maybe I just didn't understand the continuous nice loop to its full, like everything you can get out of it.
Yeah.
But I feel like in my head, I didn't recognize that row 1, column 1 and row 9, column 9 must be the same value as each other.
Yeah. And the continuous nice loop does end up showing that. But it's not as obvious, I guess. You kind of have to follow the loop around.
Yeah. I guess if you think about the two strong links that we have, it is relatively obvious, actually.
Yeah. But yeah, set just gives you that.
Right.
There's another example of which I'm not going to show. I'm just going to mention it briefly. There was a puzzle a while back on Cracking the Cryptic, and it had a particular technique which Simon referred to as Schrodinger cells. And you did a puzzle, I believe it was tattooing pod racing, I think.
Which one? Yeah, I did do tattooing pod racing. Had the overlapping kites?
The kites, yeah.
Okay, yeah.
The same thing. That's what the Schrodinger cell technique was.
Right.
Turned out. So in that case, it was a continuous nice loop, just made up of overlapping kites. And it actually works differently there. The two cells that are overlapping have to be from those digits, but they're different digits. So you end up with sort of a separated pair.
Interesting.
And there are cases where you can have what's called a remote pair. Let me just get rid of all this. So let's say we had a 8-9 here.
Yes.
And we had an 8-9 there. This is a very obvious example of a remote pair. We'll do coloring.
Yeah.
Let's color that red. That's blue. That's red. That's blue. So these two are different digits.
Yes.
But they're both from 8-9. So one of them is an 8 and one of them is a 9. You can get the same idea with a bunch of different setups.
Right.
And it comes up in, I keep clicking on that, comes up in continuous nice loops frequently. You can do that as set. And the reason I'm not showing it is if you generalize it like this with the strong and weak links, it works, but it's pretty messy. You end up with a lot of double counted cells. There's actually a simpler set that Sam came up with that's imbalanced and that doesn't generalize, but it is a much more elegant way to look at that particular set. So even with what we're talking about here, there are multiple ways of doing most of this.
Yeah. So I don't know if you're going to like this question or not, but I'm going to ask it anyway. The continuous nice loop, I can't say that the one that you're presenting here, this contrived example, I can't say that it actually works in a Latin square, right? Because you need the boxes to create the strong links for that one.
Yeah, this doesn't work in a Latin square.
Yeah. But the boxes you used aren't the ones that are needed for the CNL. So it kind of feels weird that those boxes are used in the set. I don't know if I'm making sense, but like if you had the setup using just rows and columns for your strong link and your weak link, that works in a Latin square. But then your technique of using the boxes as an additional part of the set doesn't apply to Latin squares, and that just feels a bit weird to me. I don't even know if this has turned into a question, but is there a way to do it without using the boxes?
There may be. I haven't figured out what that is yet. The problem is set is very much based in adding and subtracting complete sets of 1 to 9. Right. So when you're looking at just one cell, you kind of have to add some house, right? That includes that cell. And since we're already using row 1 as a weak link, and we're already using column 1 as a weak link, we only have one choice for what we can even try. it happens to work in this case. It happens to work in the Schrodinger cell case. It happens to work in some other cases that I've looked at. I haven't quite sat down and rigorously proved that it always works.
Gotcha.
One other case, just get rid of all this again. What happens if you have something like this, where our strong link is in this cell,
yep,
and our weak link is here, and then our strong link is here, and our weak link is here. Now we're using weak link in a row and weak link in a row connecting to the same cell.
Yeah, it just doesn't feel SETI to me.
Yeah. The way you get around this, I think, is this is an ALS.
Yeah.
And we know from the ALS there's a strong link between the 1 and the 4, right?
Right.
So there's probably something you can do with that to get around it in this case. But yeah, I said,
I almost feel like it's almost asking to add the same row twice to the same set. You just double count.
You could try that, yeah. The question is, what do you do with the strong link?
Right.
Here. Do you add the column and the box? Maybe.
Maybe. I don't know.
So, if anybody's interested in experimenting with that, let me know.
Yeah.
Let me know how it works
Talk
out.
to us on the Discord.
All right. I don't know how we are on time. How are we on time?
We've been an hour, so
okay.
We can go another 15 to 30.
I will briefly bring this example up, which looks scary, because it is scary.
Yes. Yes, this notorious puzzle.
So, this is Groot Force.
I'm going to warn people before you even start talking. We don't know how to solve this puzzle, other than extreme bifurcation is what I call it.
Right. So, this is one of the puzzles that came about in my search for hard puzzles.
You found one?
I found one. This one in particular caught my eye because there are several ways that I rate puzzles. And when I say there are several programs that I use to rate puzzles.
Right.
One of them is Sudoku Explainer, which we've talked about SE ratings briefly, maybe. This is very high in that regard. But it's also particularly high in a couple of other ratings. And it's also a diamond puzzle, which I haven't explained here.
No.
So there are three types of Sudoku Explainer ratings that you can think about. Think about the overall rating.
Yeah.
So what is the hardest step that I need for this puzzle?
Okay.
This is 11.5. The hardest known classics are 11.9. So this is up there.
Right.
You can talk about the Pearl rating. The Pearl rating is the hardest technique that you need to be able to place a digit. Just one digit. Pearl rating of this is also 11.5. And then the diamond rating is the first technique that you need. How hard is it? And this is an 11.5 diamond. It's a 10.0. But 10.0 is still... we're bifurcating.
Yeah.
Unless there's some set argument, we're bifurcating. Right.
Right. Or some other technique we haven't discovered.
Or some other exotic technique. Yeah. But 10.0 is hard. And as far as I know, nobody has solved this. I haven't posted this in a place where the really masochistic people will try and solve hard puzzles. You do need to be extraordinarily masochistic to attempt this puzzle. Yes. Even using set. The reason I bring it up is we were wondering, can we use set on this puzzle?
Yeah.
And the answer is no.
But it's still interesting.
As far as we know.
Yeah.
And the reason I know that immediately is there's a measure that Mitchell Lee came up with called the fractional dimension. I am not going to get into explaining what that is. Supposedly there's a video from Mitchell coming out about this, and maybe when it comes out we'll link it. But the fractional dimension is a measure of the puzzle that I'm not going to try and explain further than that. But it has the property that if the puzzle is solvable using only singles and tuples and pointing and claiming and fish, even Franken and mutant fish, as long as they're not finned, continuous nice loops, set, some other stuff that I'm forgetting, a few other things. If it can be solved with that collection of techniques, which all fall under the umbrella of rank 0 logic. So I assume they can all be duplicated with set. Haven't gone about proving that totally, but if it can be solved with those techniques, then it has a fractional dimension of 0. And what that means is it has a unique solution as a classic puzzle, but it also has a unique solution as a fractional puzzle. Which is, it's a neat concept. It's far outside the scope of this video.
Yeah, not covering that. Although now we've...
The reason I bring it up is he put together a program to calculate the fractional dimension. So I ran this on a bunch of hard puzzles, including this one, and it has a fractional dimension of not 0.
Not 0.
So it is not solvable by basic set. It is not solvable even by mutant set, which is what I call what's in this puzzle, where you're using some additional box logic to get it to work. But we were still wondering, is it solvable using some sort of extension of set? So we talked about finned set and ripples in the fin jellyfish puzzle. And in that case, we had 1 degree of freedom. We've seen we can have 4 degrees of freedom and still make use of other information and potentially have a working set. So I put this example together. This is a set in this puzzle that only has 1 degree of freedom. There are 8 digits from 3, 4, 5, and 9 in red. And there are 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 digits from 1, 2, 6, 7, 8 in blue. Those are our blue digits. And this is an imbalanced set. So I have 5 rows in blue, and I only have 4 columns in red. And if you remember from earlier, we need 21 digits when we have that. And we only have 20. We have 8 plus 12. So another way of looking at that, we have 8 red digits. Mm-hmm. We need an extra set. So we need 12 total. And we have 13 empty blue cells.
Right.
So what we were wondering is, can we do anything with that? We only have 1 degree of freedom. But unlike in our earlier example, that degree of freedom is not restricted. We only had 1 blue cell originally in this, and we have 13.
One of them's a fin, right?
Yeah, so, David and I were talking about this. We actually had a little Zoom call to talk about this, just so we could see visuals.
If little is like 2 hours.
It was long, and I was tired.
Yes.
But it was worth it. So we took to calling these fins as well. Maybe we'll come up with a better name.
Yeah.
But it's basically the degree of freedom. So we know somewhere there is either a blue digit in blue, accounting for our degree of freedom, or there's a red digit in red, accounting for our degree of freedom. Maybe it's this 3 up here. That would account for our degree of freedom. And if that cell were a 3, then we could conclude that none of the other red cells are from 3, 4, 5, 9,
Right.
and none of the other blue cells are from 1, 2, 6, 7, 8.
Right.
Which would be a lot of information. That would get rid of a lot of pencil marks. That cell isn't 3. But if it were, that would be our degree of freedom. So we're calling that a fin.
Yeah.
And it's not the cell in this case. It's the candidate. So the candidate 3 in row 1, column 1 is a potential fin for this set. There are a bunch of them. 3 is in this cell. 5 is in that cell. 4 is in that cell. 3 is in that cell. 2 in that cell. So on.
Right.
There's a lot of them in blue. And we know which one is right because we've looked at the solution.
We had a computer tell us the solution, and we know which one the fin is.
We know which one the fin is. But it's kind of an open question. Can we do something with that? And one of the things you were looking at was these cells, right?
Yeah.
If we could show that... If we could show that this is not possible. So if those are not all red digits, then we know one of them is a blue digit. So we know that digit is the fin.
And the reason we're targeting this is twofold. One is it's cheating because we know the fin's in there. But the other reason is because this makes a quadruple. It's the only place you can make a quadruple.
Right.
In any
and there are
cells.
There are 4 red digits.
Yeah.
And yeah. So we can make a quadruple using all 4 of the red digits here. And you can, if you start from this assumption, you will eventually get a contradiction showing that one of these cells is the fin. And I don't remember, was that enough to solve the puzzle?
I don't think so.
Not quite.
I don't remember exactly. I think
the conclusion
might be, but
I think the conclusion was if we knew the cell that was the fin.
Yeah, if you know
the candidate.
If you know the correct cell that is the fin, and you eliminate 1, 2, 6, 7, 8 from it.
Other way around, I think.
All right, you eliminate. All right, You eliminate 3, 4, 5, the red
9.
digits from it. It's this cell.
It is that cell.
If you get it down to just 2, 7, then that's solvable.
Yeah, the confusion is we could just as easily have put this in red.
Yeah.
Oop. And now we have a balanced set. And we still have 1 degree of freedom.
And now we've moved the fin.
Now we've moved the fin. Can't be here anymore because it's not even in the set.
Right.
So now the fin's here, which is in red now instead of blue. But that's because we added that to red and removed it from blue.
Right.
Anyway. So there's something here. It's a lot of information to know that only one of these 20 things is true. I think there were 20. And in fact, what we were looking at using your solver is if we add all of those as weak links, does that tell us anything? And it did give some contradictions, right?
Yeah. So my solver by default, which with my experimental implementation of AIC, it's not as good as some of these other solvers, but it'll do a lot of stuff with AIC. It literally says no logical steps found. It does nothing.
Yeah.
And that's part of that rating of what's your first step at all is a 10.0 rating, right? And my solver can't do 10.0 stuff.
10.0 is disgusting.
Yeah. No, the brute force solver can solve it, but we're talking about the logical
brute force.
stuff.
Yeah.
But if we go through and we say, okay, based on this set, because we know there's only 1 degree of freedom, we can create a bunch of weak links saying, well, if a 3 is in row 1, column 1, then we can eliminate all the red digits from all the rest of the empty red cells. We can do that for every single empty cell in the set. If we do that, then my solver's able to do some stuff, but it's not able to solve it.
Yeah, I think specifically one we were looking at that was actually really easy to see.
Yes.
Is if that's a 2, if that's our fin, then we can't have a 1 in that cell anymore. And now the only place for a 1 is there.
Right.
And we can't have a 6 in any of those cells. So the only place for a 6 is there. And now we can't put a 2 anywhere in the column.
Right. So that was one of the
contradictions
found by my solver.
Yeah.
Using those weak links, which is really interesting.
Yeah, so you can eliminate a 2 using the fact that this is an almost set. You just can't eliminate all of the fins.
Right.
Well, obviously you can't eliminate all of them because one of them is correct, but you can't eliminate all but one of the fins.
You can't narrow down to the correct
You can't eliminate enough of them to make it solvable.
But it could be like a way to possibly hand solve this by targeting like where you want to actually bifurcate.
Right.
But you're still bifurcating.
Yeah. Or there's something else to discover.
Yeah.
Which maybe we'll get inspired and look some more, or maybe some of you will have some ideas.
Yeah. We're not claiming to know everything about all of this.
Not yet.
It's very interesting. It's just not there yet. So
not yet. We'll get there.
Yeah.
All right. So that's all I have as far as new content.
Right.
So one puzzle for today. Well, it spells Zoe.
Zoe. Okay.
Yeah. Zoe is my daughter. And I set this puzzle while she was asleep on the floor.
Mm-hmm.
She's 2. It is called Zoe's Puzzletime Funtime.
Nice.
It's a pretty nasty puzzle if you don't know how to solve it. And we did not go over specifically how you can use set to solve this.
Oh no. Have fun, everyone.
So much like Garam Masalas was sort of a preview of this episode that we posed as a challenge. This is a preview of a future episode. And I'm not even going to say which episode it is, because that would spoil one way to solve it. But it can be solved with set. It's just a sneaky way of doing it.
Okay.
So that's one for you to try, and we will go over that in a future episode. It might not be the next one. It depends on what we do. So
yeah. So actually, leave a comment. Are you tired of set yet? If so, we can do an episode on something else first, and then go back to set. Or do you want part 3 of set right away? Or like you love set and you just want this podcast it's not a podcast. This discussion to be only about set for a while. So leave a comment or talk to us in Discord if you have an opinion there.
It's secretly a podcast. Don't tell anybody.
Don't tell me.
If you made it this far in the video, don't tell anybody. But it's a podcast.
It's a podcast that's only on YouTube and requires a visual medium. So there
right.
you go. So yeah. So this is one of the puzzles. Do you have another puzzle for us as well, or is this it?
Just this one.
Okay.
And per your comment about what we do next, I do have the next set episode basically ready because I've already written stuff about this puzzle in particular and some other related things. But I do have some ideas for other things we can cover. So whichever you guys want us to do, that is totally fine.
Yeah. We're going to keep making these episodes. We're going to keep making these until...
We like talking about Sudoku stuff. So
we're not going to run out of stuff to talk about. The question is what you would prefer to have next. Do you want a break from set? Or do you want to just keep on chugging and do as much as we can with set first?
Yeah.
So thank you, everyone, for watching through this whole thing. Hope you enjoyed it, and feel free to watch it again if you didn't catch something. Let us know if if I wasn't good enough at asking the right questions. If you do have questions, or you'd like me to chime in more often with questions, all of that stuff, just any feedback on how we present this is awesome, positive or negative, as long as it's constructive. And we will see you again in about 2 weeks.
Yeah. Thanks, everyone.
And don't forget to subscribe. And
ring the bell
and join us when I stream.
Did you know only some made-up percentage of people who watch this are subscribed?
I'm not going to bother you guys with those stats because I don't know how accurate they are. YouTube loves to tell me that I have a bunch of non-subscribers watching, but they might open the video for 2 seconds.
We are happy for anybody to watch.
Yes, exactly. But if I do hit 1,000 subscribers, it unlocks a bunch of stuff on YouTube for me, and I would like to have that as my shiny new toy. So if you can help me with that, that's awesome. And I also have a Patreon that if you'd like to join it, it literally does nothing except give you access to a channel where you can brag that you have my Patreon. It's mostly for people who decided they wanted to support the content that I create, including this discussion, as well as my streams and the videos I create. So if you would like to support me, feel free to do so on the Patreon.
I don't have any such thing, but I hang out on the CTC Discord and on David's Discord. And if you have questions about Sudoku, let me know.
Philip loves to be pinged, so just go ahead and ping him.
I get pinged all the time.
Yeah.
It doesn't bother me.
All right. And we will see you next time.